Today we'll be talking about conjugated dienes and one of the reactions they undergo, electrophilic addition. Conjugated dienes are two double bonds separated by a single bond, and these systems are more stable than normal alkenes because the electrons are delocalized over the entire system. This will become evident when we look at electrophilic addition and see some of the resonance structures formed. With dienes, we could get different products based on the different conditions. So a kinetic product is formed at lower temperatures and doesn't have enough added energy in the form of heat to push to the most stable alkene, which is the most substituted alkene. So it settles for carbocation stability. With heat, we have added energy to the system, and it pushes it through the activation energy barrier. So with heat, we're going to have an equilibrium between the kinetic product and the thermodynamic product because there's enough energy there for the both of them. However, because the more substituted alkene is the more stable product, this will be our major product under thermodynamic conditions. So we have a nucleophilic double bond that will donate to our electrophilic hydrogen. Now the question is, where's that hydrogen going to go? That 1 or 2 position? Well, that hydrogen is going to go to carbon 1 for 2 reasons. 1, we get a more stable positive charge on a secondary carbon instead of a primary carbon, and more importantly, we get a resonance stabilized positive charge. Now looking at the resonance structures, we can see how the reaction can involve the entire molecule. You can also see that one of the resonance structures has that carbocation on a primary carbon. This is what I was talking about in terms of the transition state being higher energy but resulting in a more stable alkene for the thermodynamic product. So that allylic cation will now trap that nucleophile, the bromide. Under different conditions, we'll get a different product. So with heat, we're going to get the thermodynamic product, or the more stable alkene. Under kinetic conditions, like cold or not giving the reaction very long, we're going to get the more stable carbocation and the kinetic product. And remember that this process is non-stereoselective and that nucleophile can come from either side of the carbocation. Pause now to try this problem on your own. It's a hard one. You should look at the resonance structures to see where that initial electrophile, the hydrogen, will land. Remember, we want the carbocation to be delocalized by the other double bond, so there are 2 positions that make this possible. Because we're looking for that kinetic product in this case, we want the more stable carbocations. We see a secondary and tertiary allylic cation for one, and a secondary allylic cation for the other. So whichever has the more stable cations are going to be the structures we will utilize when determining this kinetic product. And with the kinetic product, the major product will be the one with the most stable carbocation, and this will trap the nucleophile.